Hello everyone, today we will learn about the parity of functions. Before this lesson, we obtained the monotonicity of a function by studying the relationship between the size of the independent variable and the corresponding function value in a certain interval of the domain, and used symbolic language to succinctly and accurately describe the property of the function graph rising or falling in a certain interval of the domain. In this class, we will continue to study another property of functions. Before class, everyone has already drawn several function graphs. Now, please observe that fx equals x squared and gx equal the absolute value of x absolute value. Do these two function graphs have any common features? It is easy to see that both function graphs are symmetrical about the y-axis. And this conclusion is only based on the intuitive representation of the letter image. So can we analogize and study the monotonicity of functions? What about reflecting the properties obtained from intuitive function graphs through the relationship between independent variables and corresponding function values? Or can we reflect the properties of graphics through quantitative relationships? Let's take a look at this table together. Firstly, we fill in the corresponding function values in the table. When x is -3, the square of x is 9. When x is -2, the square of x is 4. And so on. We then fill in all subsequent function values in the table. Now please observe this table. Can you find any quantitative relationships? Some students may have already seen that f-3 is 9, f3 is also 9. These two values are equal. f-24, f2 is also 4, and these two function values are also equal. That is to say, we found that when the independent variable takes a pair of opposite numbers, the corresponding two function values are equal. So please think about it. We found that all the points in the table have the above properties. Do other points not listed in the table also have the same properties? For example, are f-1.3 and f1.3 equal? This conclusion is clearly affirmative. In fact, anything belonging to R, f-x equals -x squared and fx equals x squared is equal. The function with such characteristics is called an even function. The process of proving the conclusion with a function analytical expression just now is essentially using symbolic language to characterize the properties of the function. Okay, let's go back to the process of studying the monotonicity of functions at that time. We go from the intuitive rise and fall of the function graph to the qualitative conclusion that y increases or decreases with the increase of x, and then to the rigorous quantitative expression. So, may I ask everyone, can we analogically study the monotonicity of functions and use symbolic language to express the feature of function graphs being symmetric about the external axis? We just mentioned that when the independent variable takes a pair of opposite numbers, the corresponding two function values are equal, which means that the function value of -x is equal to that of x. So we can generalize this conclusion with the knowledge of middle school axial symmetry. Let's take a look at the definition of even functions together. Generally, the function fx is defined as I. If any x belongs to I, there is a negative x belonging to I, and f-x equals fx, then the function fx is called an even function. So we have the definition of even functions. So let's take a look at another set of functions. The graphs of the two functions just now are symmetrical about the y-axis. The graphs of these two functions, fx is equal to x and g is equal to 1/10 of x, do they have any common characteristics? It is easy to see that both function graphs are symmetric about the origin. So, we also obtain this conclusion from an intuitive function graph. Can we compare the research process just now and explore this conclusion through quantitative relationships? Let's take a look at this table together. We also fill in the corresponding function values in the table. Can you observe any quantitative characteristics in this table? Perhaps some people have already noticed that this time we will look at the function gx equal to 1 over x, g-3 equal to -1/3, and g3 equal to 1/3. These two functions have opposite values to each other. g-2 equals -1/2, g2 equals 1/2, and these two function values are already a pair of opposite numbers to each other. We found that when the independent variable takes a pair of opposite numbers, the corresponding two function values are also a pair of opposite numbers. Moreover, other points not listed in the table must also have the property of being an upper number. For example, f-1.3 is definitely equal to -f1.3. The function with such characteristics is called an odd function. Okay, please think about it. Can we define even functions and rigorously express the characteristic of function graph symmetry about the origin in symbolic language? Let's take a look at the definition of odd functions together. The general definition of the function f(x) is I. If any x belongs to I, there is a negative x belonging to I, and f negative x equals the negative f(x), then the function f(x) is called an odd function. In this way, we have obtained the definitions of even and odd functions. So let's delve deeper into these two definitions. I will present the definitions of even and odd functions on the screen. May I ask your first question? How do we understand that any x in the definition belongs to I, and there is a negative x belonging to I? We found that both definitions have such a part. The most straightforward understanding is that if you take any independent variable from the domain, its opposite number is still in the local domain. That is to say, he told us that the domains of odd and even functions must be symmetric about the origin, which is also the primary condition for us to determine whether a function has parity in the future. Okay, can any of the definitions be removed? Why? This conclusion is clearly negative. In fact, the parity of a function is different from its monotonicity. The monotonicity of a function may only be a property of its increase or decrease over a certain interval, but the parity of a function must reflect its overall properties. That is to say, he requires any independent variable in the domain to have such characteristics. The third question, can you summarize the similarities and differences between odd and even functions? Just now, we talked about two similarities between odd functions and functions. Let's take a look together. The first similarity is that the domains of odd and even functions must be symmetric about the origin. The second similarity is that odd functions, even functions, or the parity of functions is a global property of functions. Okay, then please think about the differences between odd and even functions. Just now we found from the table that when the independent variable takes a pair of opposite numbers, the function values of even functions are equal, while the function values of odd functions are also a pair of opposite numbers. Then we found from the graph that the function graph of even functions is symmetrical about the y-axis, while the graph of odd functions is symmetrical about the origin. In this way, we have identified two differences between odd and even functions in terms of numbers and shapes. Okay, for the fourth question, there is a part in the definition of even functions where f negative x equals fx. There is also a part in the definition of odd functions where f negative x equals negative fx. So please think about these two parts in the definition. Do we have any other equivalent mathematical expressions? Let's take a look together. Sometimes we can move two function values in the definition to the side of the equal sign to obtain the equivalent form of the definition. Let the function fx be defined as I. We have fx as an even function, which is equivalent to any x belonging to I, negative x belonging to I, and f minus x minus fx equals 0. Similar, fx is an odd function equivalent to any x belonging to negative x belonging to 2, and f negative x plus fx equals 0. The above form can be very useful in determining the parity of certain functions. For example, after calculating f negative x, if we cannot intuitively determine whether it is equal to fx or an opposite number, we can compare the result of the sum or difference operation with 0 to obtain the conclusion of whether the function has parity. After exploring the definition of odd functions, let's determine the parity of several specific functions. The first, fx is equal to the fourth power of x. Let's take a look together. Firstly, we will solve the function domain, where fx is equal to the fourth power of x. The domain of this function is R, which is a symmetric domain about the origin. Let's use the notation in the definition, where any x belongs to R, there is a negative x that belongs to R. Okay, next let's substitute f negative x into the analytical expression of the function. It is equal to the fourth power of negative x, and fx is equal to the fourth power of x. According to the definition of even functions, we can conclude that function fx is an even function. So please think about it. If the analytical expression of the function remains unchanged, but an additional domain constraint of xo is added, is the function gx still an even function at this time? This function is obviously not an even function anymore. At this point, the domain of functions g and x is an open interval from 0 to positive infinity, and this domain is not symmetric about the origin, so functions g and x do not have parity. Okay, just now we rigorously proved that the function fx is an even function equal to the fourth power of x. Can we summarize the steps to prove the parity of a function from the process of solving the problem just now? Let's take a look together. According to the definition of odd functions, we can determine the parity of a function by following the steps below. The first step is to find the domain of the function, and then we need to determine whether the domain of the function is symmetric about the origin. If the domain of the function is not symmetric about the origin, we can directly conclude that the function f(x) does not have parity limits. If the function law is symmetric about the origin, we proceed to the next step of calculation, where f is negative x. Okay, step 3. Any x belongs to I, where I is the domain. Calculate f negative x. Okay, if f negative x equals fx, then the function fx is an even function. If f negative x equals negative fx, then the function fx is an odd function. If neither of the above holds, then the function fx is neither an odd nor even function. If both of the above equations hold, then the function fx is both odd and even. Okay, a special reminder to everyone that when we prove that a function is an odd or even function, it must hold true for any independent variable in the domain. But if we prove that a function is not an odd or even function, we only need to give a counterexample. For example, if we know that f3 is equal to f negative 3, we cannot deduce that the function fx is an even function. However, if we know that f3 is not equal to f negative 3, then the function fx is definitely not an even function. Okay, so we have a general method for determining whether a function has parity. Next, we will use the method we just explored to determine the parity of the following functions. The second one is that fx is equal to x plus 1/10 of x. We also first calculate the domain of the function, and based on the condition that the denominator is not 0, we obtain that the domain of the function fx is x, which is not equal to 0. This domain is symmetric about the origin, which means that if we take any independent variable from the domain, its opposite number is still in the domain. Then we bring in f negative x, which is equal to the sum of negative x and negative x by 1. After we proposed the symbol, x equals negative x plus 1 of x equals negative fx. Therefore, according to the definition of odd functions, function fx is an odd function. Okay, the third one, fx is equal to the root x. Similarly, we first solve the function localization, and based on the non-negative condition under the root sign, we obtain the function localization as x, where x is greater than or equal to 0. This time we found that the domain of this function is not symmetric about the origin, which means we can find an independent variable from the domain whose opposite number is not in the local domain. So according to the definition of odd-even function we just explored, at this point, function fx is neither an odd nor even function. This also reminds everyone that if we have already determined that the function fx is locally asymmetric about the origin, we do not need to calculate f negative x. We can directly conclude that the function fx does not have parity. Okay, the fourth one, fx equals O. Similarly, we first calculate the function domain, where the function fx is defined as R. This domain is symmetric about the origin, and then we substitute f negative x, where f negative x equals 0. We found that it is equal to fx and also equal to negative fx. According to the definition of function parity, this function fx is both odd and even. So we found from the previous step that if we need fx to be both an odd and even function, then there must be f negative x equal to fx. At the same time, f negative x must also be equal to negative fx. That is to say, we need negative fx equals fx. So we can simplify the calculation and obtain that the function fx equals 0, which is a constant function. This also tells us that the analytical expression for a function that is both an odd function and a prime function must be fx equals 0. So please think about it. Are there any other functions that are both odd and even functions similar to this analytical expression? Some students may have already thought that we can impose some restrictions on it locally. For example, when x belongs to -1 to 1, our analytical expression remains unchanged, and this function is both odd and even. Alternatively, if x belongs to the left closed and right open interval from -1 to 0, then we can merge it with the left open and right closed interval from 0 to 1. That is to say, we have found that as long as the domain is symmetric about the origin and the analytical expression for the function fx equals 0 remains unchanged, then the function fx is both an odd and even function. Okay, now let's take a look at example 2. Determine that the function fx is equal to the cube of x plus the parity of x. The first step is to solve the function domain. The function fx has a domain of 2, which is a local symmetry about the origin. That is to say, if any x belongs to R, there must be negative x belonging to R. Then substitute f negative x, which is equal to the third power of negative x plus negative x. After proposing the sign, it is equal to the third power of negative x plus x equals negative fx. Therefore, the function fx is an odd function. Okay, let's take a look at the second question. You may not have drawn the graph of this function just now, but now I have provided you with the function graph on the right side of the y-axis. Can you obtain the image of fx on the left side of the y-axis through the parity of the function fx? Just now there was the first one. We have already proven that the function fx is an odd function. So, please think about the characteristics of odd functions from the graph. You should remember that odd functions on the graph are symmetric about the origin. Based on the symmetry on the graph, we can complete the entire local graph to obtain the function graph shown in the figure. Okay, this question itself is not difficult, so please think about it. In the process of solving this question, what insights did it give you? Or, if we already know that function fx is an odd or even function, how can we simplify our research on it? Generally, if we have determined the parity of the function fx, we can only study the graph and properties of this function on half of the local domain, and then use the parity of numbers, that is, the symmetry on the graph, to obtain the graph and properties on the entire local domain. Okay, let's summarize the content of this lesson briefly. Today we start with the symmetry of several specific function graphs, verify function values through calculations, and characterize the properties of functions using symbolic language. We abstract the definitions of odd and even functions and explore the general method for determining whether a function has parity. So may I ask everyone, in the last class we studied the monotonicity of functions. Today we will explore the parity of functions. What is the purpose of the parity of a function? In fact, if a function has parity, we can use its symmetry on the graph to obtain the graph of this function more concisely. And along with the monotonicity of the function, we can explore more properties of this function. Okay, that's all for today's class. Goodbye.